Alright, let's render a triangle, shall we? So how about we render this little nice purple triangle? How do we do that? Well, let's start with our simple little project that I introduced in the first part of this series, where we simply rendering a green screen, and we'll go from here. So what's the first thing we should think about? How about we start with triangle coordinates? What are they? Well, here is our screen and our triangle, and Metal internally uses normalized coordinate system. In our case, we're just looking at the x and y axis, and both of them go from -1 to 1, which means like the leftmost of the screen is -1 and the rightmost is 1 for x, and similar for y. Bottom is -1 and top is 1. And so in our triangle we will have 3 vertices sitting at roughly these coordinates. So let's try coordinate. Going back to our project, we have this draw method where we just set the screen color to green, and so let's input our vertices. So how will it look like? Let's do just a simple array, floats, and initialize it. So Metal is a 3D first API, and so internally it assumes that all vertex coordinates have 3, well, x, y, and z coordinates. In our case, we don't really use z for now, just x and y, and so we will use 0 for that. So, and according to our picture, first one is this. That will be that. Second one, this. Zero for that, and the last one, this one. Should be comma here. Okay, 0. Alright, here we go. Notice that we use just a one-dimensional array, and we simply input vertex coordinates back to back, one after another after another. Okay, something is wrong here. What's that? Is it because I need to add vector here? Probably, right, yeah, exactly. So how do we pass those, well, let's think about next steps. So how do we render it on screen? Well, we should actually just pass it to GPU and say, hey, render it. So that sounds simple, right? Yeah, of course. So the only thing we need to do is to pass them to GPU. Well, how do we do that? Well, Metal has buffer data structure, which is essentially just some region in memory that we can put some data onto, and GPU will access it. So it's a fairly simple concept. Let's see how we can do it. So to create a buffer, let's call it P vertices. We need to take our device and call new buffer method, and in our case we will use this overload. We should just pass a pointer to our array of data. In our case that would be this. Now length is how many bytes our data takes, and that would be size of one float times 9, because we have 9 different floats. So let's do that. Size of float times 9. And then the resource options is to which memory we should put this this data. Essentially, there are different options. For example, you could go with private mode, where you say that data is going to be only accessible by GPU and CPU will not have access to it. But in our case that's not the case, because we actually populate this buffer on CPU side right now and only then pass it to GPU. So in our case we need both CPU and GPU to have access to this data, and so we'll use a shared mode, and that's pretty much it. And the tricky thing is that we of course get back a pointer to buffer, and at some point after we're done we should release it as usual. And this is the approach that we have been using so far, but it's actually error prone, of course, because if you forget to do it, then you get a nice little memory leak, and that's kind of not fun. So we can probably use a better approach, which is using C++ smart pointers. And in our case it's going to be a little bit trickier, because we will have to provide a custom deleter for smart pointer, because usually when there are no more references to the object, then the pointer will simply call delete on that object. But in our case that's not what we want, because we have to call this specific release method to deallocate memory, and so we'll have to provide a custom deleter. And so how do we do that? Well, that's going to be a little bit long, but bear with me, it's C++. And first argument to the constructor would be call to our factory function, and second one we will specify a lambda function that will be called to release memory, like that. A little bit long, hard to read, but that's what it is. You get to it, get used to it. So that's the same thing. And then next, as with everything, we need to ask our render command encoder to pass this buffer to GPU, and there is this dedicated method for that, set vertex buffer. So here we simply pass our buffer and then offset in buffer from where the data starts, in our case from the beginning, so that's 0. And then index is basically the GPU has a limited number of buffers that you can use. It varies depending on the device. Let's say iOS device would have less buffers than macOS. I think maybe, don't quote me on that, but for iOS I think it's probably about 16, and for macOS it might be 32 or 64, something along those lines. So basically, let's say you have indexes from 0 to 15 at least, so you can pass at least 15 different buffers per frame, well, depending on the device again. So in our case, how about 5? Let's go 5. And the next thing, remember we said we just ask GPU to render that, right? So that sounds easy enough. How do you do that? Well, let's do draw primitives. That should do it. How about the simplest thing? Primitive type. Well, we need triangles, so let's do that. And vertex start. That would be 0, right, from the beginning. And then how many vertices? Well, we have 3 vertices, so let's do that. So we have to use this little ugly integer wrappers to pass integers, because again we're dealing with this Objective-C runtime, and so we have to go through hoops a little bit to satisfy the API. Essentially just integer, kind of boxed integer. That's fine. Okay, oh, of course, right, because we're passing pointer, but it wants the raw pointer, so we have to get the raw pointer here. Alright, that's alright. Yeah, kind of. The next thing that we need to do is to actually write some nice shader to deal with the vertices that we get on GPU. So how about we do that? Let's do metal file, let's call it shaders, and that would be, so we will need to write 2 different shaders for that. So one is vertex shader, which will be executed for each vertex to transform its position, and then another shader that would be a fragment shader, which essentially will tell us which color each vertex, well, not even vertex, but each pixel inside of our triangle will be. So we'll talk a little bit more about that as we write them. So let's get started. Say first we need to use this attribute to specify that it is going to be a vertex shader, and then we do specify the return type, which is float4, and for GPU it means that if vertex shader returning float4, essentially just 4 floats, and it's essentially just a position of a vertex, because vertex shader is going to be executed for each vertex that we pass to GPU. And so as we transform the position of each vertex, and then we just return the transformed position as a float4. So 3 floats there, x, y, z coordinates, and then also a w, which we will not go into details about in this video. So what are the method arguments for vertex shader? Well, that would be our buffer of vertices. Let's do constant device, well, constant float pointer triangle vertices, then buffer 5. So that's some mysterious syntax. So let's go step by step. So what is const? Just a normal C++ const means constant. Then this constant keyword, it has to do with Metal APIs. It's basically address space. There are two different address spaces. One is constant, another one device. And the difference between them is that device is a memory to which you can both read and write, and constant is the memory from where you can only read. And so in our case we will be simply reading those vertex coordinates and we will not write into it, so I use constant. Then type, we send floats, and so our type is going to be float, obviously, right? Okay, and then buffer 5. This is the attribute that tells GPU which buffer we used to send data in. It's the index of the buffer. So remember, in our renderer we use this 5 buffer of index 5, and so GPU we have to use the same number to get those vertices. And so the next interesting thing that we need to think about is, so now okay, we pass this array of ours, let's copy it here and just comment it out. So we have this 9 floats, and the shader is going to be executed for each vertex in parallel. So we pass 3 vertices, and so this vertex will be called 3 times, and each of those executions will get the same 9 vertices. And so we need to have some sort of way to index into this array and say something like, okay, so for first vertex I want to start from the 0 position in the array and read 3 floats, and that would be my vertex. And then for another vertex I need to start at this index and read another 3 vertices, and for the last vertex I need to start at this index. So we need some sort of mechanism to index into this array depending on the vertex that we are dealing with. We can use this vertex ID attribute to ask for vertex ID to be passed as an argument to our vertex shader, and we can use this vertex ID to index into this array. So the way it works, we have 3 different executions of our vertex shader for each of 3 vertices, and Metal is smart enough to be able to separate different vertex coordinates from a single array that we pass in, because each vertex obviously has 3 coordinates. And so, for example, for the first vertex that index would be 0, and then for second vertex that index would be 0, 1, 2, 3, and 3, 4, 5, and for the last one that would be 6, right? And so since Metal is doing all this heavy lifting for us, we can probably do something like this. So that's why then the value after that would be x, and value after that y, and value after that z, right? So this is true assuming that whether vertex index is this or this, we will get correct vertex coordinates, right? Well, that sounds good in theory. So let's give it a shot. And then we need to return this as float 4. So we return our coordinates and then 140W. Alright, that looks good enough. So the next thing we need to do is to write this fragment shader. And so again, let's think about what happens in the rendering pipeline. So at this point we just returned coordinates of vertices transformed somehow. Well, in our case we're not transforming them in any way, just returning them as is. But then what happens next? Well, after that what happens is rasterization, where our scene, which could be 3D, right, it's going to be mapped on our 2D screen somehow. And the algorithms that modern GPUs use is called Z-buffer rasterization, which will not go into detail in this video how it works, but essentially just a good way to think about it is that it takes 3D scene and it just maps it on your 2D screen. And that's all it does. And talking about our triangle, here we had just 3 vertices, but GPU will do all the hard work to identify each pixel that this triangle consists of, and so it will basically turn this entire triangle into a bunch of pixels. So it will know which pixels will correspond to this triangle after rasterization. And so what fragment shader does, as an input it receives a coordinates of a single pixel, and so pixels are, you probably know that those are kind of these little squares. Well, in fact pixel is just a color sample at the center of this little square and not the square itself, but for simplicity you can probably think about it that each pixel is a little square. And so there is a lot of little squares that will be part of this triangle, obviously. And so fragment shader receives a coordinates of a single pixel, and as an input, and as an output you should return the color of that pixel. So as an input you get coordinates of the pixel, and as an output you should return color. So that sounds simple enough, right? Well, for our program it's going to be really simple. And so another interesting thing to think about is that vertex shader, we just had 3 shaders executing in parallel for each vertex. So in the case of fragments we're going to have much more than just 3 shaders executing in parallel, because again we need to execute a shader for each pixel, and there are much more than 3 pixels here, right? Probably a few hundreds, maybe 100 at least, something like that. So those are going to be executed on GPU in parallel. So as we discussed, as a return we need to return the color of a pixel, and the color is going to be in as a float 4, and that represents RGBA, right? Red, green, blue components and alpha, 4 components, 4 floats, float 4. And then fragment shader, and in our case we want what? Just purple triangle, so basically all pixels that are inside of the triangle going to be purple. So we'll do red 1, then green 0, and then blue 1. That should give us this nice purple, and then alpha value 1, which means fully opaque, not transparent at all. And in fact, actually, even if we set it to not to something, even if we set it to 0, then it's not going to be transparent because we didn't enable blending in our rendering pipeline. But again, we are not going to get into this topic for this video. So this value basically doesn't matter, but we still need to provide something for that value. Alright, so that should do it, right? Well, kind of. Now we also need to do some interesting, more like boilerplate, to be honest with you, work on GPU, because we actually need to tell GPU somehow, and more accurately, we need to tell render encoder which shaders to use. Okay, so on GPU we can have many shaders, right? We just wrote 2, but in fact we will, in the real application, we need to write many more than that. And so we need to, there is a mechanism so that we need to use to tell render encoder which pair of vertex and fragment shaders to use. And so for that we need to create what is called render pipeline state, and that render pipeline state we will need to associate with the shader functions by name. So we're going to create this render pipeline state, and we're gonna say, okay, so for vertex shader use this function with this name, and for fragment shader use that function with that name, and then we will say render encoder we will associate render encoder with a render pipeline state that we will create. And so there's going to be this render encoder, then pipeline state, and then pipeline state knows about functions, and so that way render encoder knows which functions to call. So that's actually not that complicated, but there's quite a bit of code that we will need to write, so let's get into it. So first let's add a new field to the class, and that's going to be this render pipeline state that I just mentioned. Then in a similar fashion we are going to use a smart pointer to hold it so that we don't have to call the release method manually when we're done. So we added that. Now let's use our initialization list to call that, to initialize that. So that okay, yeah, that's right. So as usual, in the initialization list, following C++ best practices, we initialize it to null pointer for now, and then also provide a destructor, our custom destructor, custom deleter. And then let's also, to not clutter our draw method call, let's also add a new function, new method that we will use to create this render pipeline state and associate it with shader functions. Let's call it just build shaders. How about that? And then implementation of that function would be this. Wow, a lot of code, right? Don't worry, let's go through it step by step. So the first thing we do, we create a new metal library by calling a new default library from our PDYs. And what it does essentially, it takes all the shaders that we have. We just have one metal file, but we could have many metal files, and each of them could have different functions. And so what default library does, it just takes all the functions that we write and put them in a single file. That's a really nice way to think about it. So it puts all the functions, all the shader functions in a simple file. And so from that point on, it can look at the single file, look at the name of the function and find it, right? So library can do that. The next thing, we need to create our functions. Basically, you just get a handle to our function somehow, right? And so there is this metal function class, and we can create it using our metal library that we got, right? So we use this. We can create this function using this new function method call. And so, like I said, what we do essentially, we just tell the name of this function. In our case, that's vertex shader. This is the one, right? So we use that, and then we get back the pointer to our function. So it's just a handle of this function. And then the same thing we do with fragment shader. We call new function and we say, okay, here's the name of my shader function, that's fragment shader. And so we get these two functions here, p vertex of n and p fragment of n. And so the next thing, we allocate memory for, we need to create a render pipeline state to populate this variable that we created earlier. And so render pipeline state is created from render pipeline descriptor. You still with me? API is kind of tangled a little bit, but it takes some time to kind of get used to all the things. So okay, we're creating a render pipeline state, right? To create it, we need to have a render pipeline descriptor. And so we allocate memory for that. That's the line. Then, important thing, we say, okay, so here's the vertex function that you will use. And so we basically just call a setter and we use our handle to kind of to tell which function that we want to use, right? Our function. This is our handle, right? We just pass it to setter. So same way we do it for fragment function. And so the next thing, we need to say which pixel format we should use. So it is just a boilerplate thing because by default it's not specified, and so compiler will complain when we will get an error at runtime if we just try to run it without setting this pixel format. So throughout the video we just used this one. It's kind of just a standard when blue, green, red and alpha components are stored as a single bytes, essentially 4 bytes, byte for each of those components in BG array order. So it just tells the API that, and then we get those 3 things in place, and we simply call new render pipeline state. We pass our render pipeline descriptor, and finally we get our render pipeline state created, and it knows that you want to use these 2 shader functions, so it's all good. And so this little thing, by calling reset, we simply update the value of this smart pointer, because remember, it's smart pointer currently, it's initialized to null pointer, and if we want to change the value, we just call the reset method. Alright, all good? You're still here? So another little thing is that when we call this new render pipeline state method, we have to also, there are different overloads, but there is kind of like the overload that we use, it requires us to also pass a pointer to an error. Basically some variable that will be set to something if we got an error. So this is like a way for us to know if during render pipeline state creation we got an error. And so if we did, then this thing will not be null pointer, it will be set to something. And so after we called new render pipeline state, we also check whether we got an error or not. And if we did, then we want to print the localized message. So just some error handling here. So that's almost another thing. We actually, in our constructor here, we need to call this build shaders function that we just implemented. So let's do that. And then one little thing here is that we need to also associate render encoder with the render pipeline state that we created. Remember, we talked about it. So we set render pipeline state, and we use our p render pipeline state raw pointer. So that's the only thing, right? Well, let's hopefully let's try running it, shall we? So let's clean this and run. What do we get? Alright, we got something, no errors. But this triangle doesn't really look like the one we expected to see, right? So we want this. We want this and we get this. We want this, we get this. Why? Well, there is another kind of a problem that we run into when passing our data. So remember, we were just passing 9 floats and we get them on GPU here, and we treat them as if they were in the same format that we passed them in, right? And so in fact that's not what happened. So let's look at this this kind of little visualization here. So when we were creating our vector with vertices, it looked like this, right? And so I'm just showing it here. So it's just 9 floats, and first 3 floats is XYZ coordinates for vertex 1, and then vertex 2, vertex 3. So simple enough. However, on GPU what happens is that we actually, the way we wrote our code right now, we actually get something like this, right? So we get our 3 floats, and then we get some garbage, basically could be any value, any number, and then we get our 3 floats for the second vertex again, and then again some garbage, and then last 3 coordinates for the last vertex, and then some garbage. And so the way our code is currently written is that we don't account for this garbage essentially inserted between vertex coordinates for different vertices, and so we just take vertex coordinates in the same way we had them on CPU. And so for the first vertex we got it right, And then, but like second vertex x coordinates, we get some random number essentially, right? And for third vertex, we get y coordinates as some random number. And so actually, if we run this again and take a look at it, so this is our first vertex, right? And it should be what? Minus 0, 5, 0, 5. So looking at this like actually looks about right? So this is the vertex with this coordinates. I could believe that. That's probably correct. So this is our second vertex, and that's what like supposed to be 0, 5, 0, 5, right? And what we get is probably more like 0, 0, 5, I think, right? And so as you see, like x coordinate is something else, but y coordinate is 0, 5. So, and that's actually what we get, right? So y coordinate is still 0, 5, because that's what it is. It's fine, but x coordinate is some garbage that we got. And so in our case, it was probably 0, right? Because I think it's probably 0, right? So it could be any number for you, but in my case it was 0. This problem happens because metal internally processes the array of vertices that we pass in, and it stores each vertex in a different data structure, and this data structure has different memory alignment. This is kind of an advanced topic as well, and I don't want to get into too much detail about it, but essentially due to memory alignment issues, each vertex in memory will start at a address that is divisible by 16, because that's the metal under the hood uses this float 3 data structure, and it has memory alignment of 16, whereas in our case we would need memory alignment at 4 to actually ensure that this vertex coordinates would start there instead of this garbage. And so you can think about it this way. So let's say this vertex starts at 0 in memory, float is 4 bytes long, so this is 0, this is 4, this is 8, this is 12. And so since metal internally uses float 3 data structure which has alignment 16, it can only place the vertex in memory at the address that is divisible by 16. And in our case, we are just sitting here at 12, right? So it is 12. And so we need to put like another 4 byte long something before we can, well, we don't put it, we just look at this, look for the next address that is divisible by 16, right? So in our case, that would be 16, which starts here. And so here we put another vertex coordinate, so that's 16, 20, 24, that's 28, right? So 28 is also not divisible by 16, and so we need to take another 4 bytes and place another vertex coordinates at this address, which starts at 32 because it's divisible by 16. And so that's kind of the reason why we get this garbage here and here. And so what we need to do to resolve this problem, we need to tell metal to use a different data structure. Not use this data structure with alignment 16, but rather use data structure where its alignment is 4. And so for that, we, instead of passing simple floats, basically array of floats, we can tell the GPU to instead pass an array of data structures, kind of array of vertices, right? So that would be packed float 3. So remember, I was telling that it uses this float 3 which has alignment 16 internally, and that's not what we want. What we want is packed float which has alignment 4, so that that garbage, this z garbage, is not going to be, like, essentially by using this data structure we just guarantee that our vertices will have the same, they will be stored contiguously in memory as we had it on CPU. So we use that, and now instead of just an array of 9 floats, we have an array of 3 packed floats. Right, so now we have this data structure and we have 3 of them because each of them has 3 floats in them. So this is data structure, right, with X, Y, and Z inside, and we receive 3 of them here, and this index that we're going to get is going to be either 0 for the first 3, or 1 for second 3, or 2 for last 3. And so because of that, the way we do it here, it's not going to cut it. It's not going to cut it. Instead, it's going to be much simpler than that, because we can just use this, because remember I said it is going to be either 0, 1, or 2, and by indexing into it we get the right set of X, Y, and Z coordinates itself. And this float 4 constructor, it has an overload where we can simply pass packed float 3 for the X, Y, and Z coordinates, and then the only thing we need to pass is the fourth one, which is W value, which is going to be just 1. And so now that we did it, it should probably work. And there you have it. So that was a nice exercise, I thought. If you guys liked it, let me know in the comments. Hit that like, subscribe to my channel for more videos in the series, and I'll see you soon.